Hello, my name is Barrutia, and I'm currently doing summer research at the University of Florida. I work in the Department of Biomedical Engineering, part of the College of Engineering. I'm a rising senior studying biomedical and mechanical engineering at Rensselaer Polytechnic Institute in Troy, New York. This summer, I've had the opportunity to work with Dr. Daniel Ferris in the Human Neuromechanics Lab. My project was named The Design of a Passive Leg Exoskeleton. The goal of the project is to make an inexpensive and easy-to-use leg exoskeleton that increases knee torque and jumping height, with the goal of fostering an interest in biomechanics in the youth. A set of constraints was decided for the design, including a maximum weight and a starting angle for the torque, a maximum torque given to each knee, a jumping height gain, and of course the rigidity, wearing, and ease of wearing. During the brainstorming phase, I came up with several ideas on how to design the exoskeleton, but ultimately decided for the parallelogram one. A 3D scanner was used to obtain the model of a boy's leg in order to build the exoskeleton around it. MATLAB was used in order to simulate the system, including the forces, the length of the rubber band, and the torque given to the knee. My initial design consisted of 5 different subsystems. They are the rubber band holder, the bars, the lower leg support, the thigh support, and the joints. The purpose of the rubber band holder was to hold several bands at the same time without breaking. Several concepts were thought of for this, but ultimately the carabiner was chosen. The purpose of the joints is to connect everything together in the system. They must be as frictionless as possible and not break at any moment. 4 different parts were chosen for this task. They are the binding barrel, the needle roller bearing, the needle roller thrust bearing, and ultra-wide flange screws. The purpose of the bars is to transfer the potential energy from the bands into the body supports. They must not buckle at any moment and be made of a durable material. 3 materials were chosen: plastic with carbon fiber, aluminum, and wood. Plastic with carbon fiber was ultimately selected as this was the easiest way to manufacture the parts. The lower leg support was designed to transfer the forces from the rubber band onto the leg. The figure to the right shows the final CAD design for this part. The thigh support was designed similarly to the lower leg support. It must also be as big as possible in order to decrease the pressure that is exerted into the leg. Computer-aided design software NX was used to build an assembly containing every part of the exoskeleton. 3D printing of the parts was performed using a Markforged 3D printer. The parts were built with plastic and reinforced with carbon fiber in areas where a higher strength was required. After several days of printing, I finally got my first prototype. Here are some clips of me walking and jumping with my device.
Okay.
There were several problems and issues when I was trying my device. First of all, the exoskeleton was sliding across and down the leg sometimes when I didn't tie the Velcro tight enough. Some of the sharp edges made it uncomfortable to wear for an extended period of time. The joints on the binding barrels will also start to bend after 10 or more rubber bands were used while jumping. And lastly, the Velcro bracket in the thigh support broke after several jams. Future work includes solving these issues, printing the exoskeleton for the other leg, and testing jump enhancement. I want to thank my faculty advisor, Dr. Daniel Ferris, for letting me do awesome research in his lab, as well as my PhD advisor, Ryan McLean, for aiding me in my research. Thank you all.